going to talk about similar triangles. So just to recap really quickly what we talked about on block day, for similar polygons, what we need for similar polygons is all corresponding angles need to be congruent, and all corresponding sides are proportional. So that's what we were using, that the corresponding sides were proportional when we did our opener. This is a lot like when we talked about congruent polygons. For congruent polygons, we said all the corresponding angles were congruent and all the corresponding sides were congruent. And then we came up with some shortcuts to show that triangles were congruent. We had side, angle, side, angle, side, side, side. So those shortcuts for our triangles. We have the same kinds of shortcuts to show that triangles are similar. So we don't have to show that every corresponding angle is congruent and every corresponding side is proportional. We have some things that are going to simplify our work. So for similar triangles, we have three shortcuts. Our first one is going to be our postulate for this section. This is what we're going to accept as true without proof. Is the angle, and we usually call it AA. Angle similarity. And angle similarity tells us that all we have to do is make sure that two angles are congruent. So we have two angles of a triangle. Are congruent to two angles of another triangle. Then they are similar. So showing that, or knowing that two angles are congruent is enough to guarantee us that all the angles are congruent and all the sides, all the corresponding sides, are going to be proportional. So let's look at a couple of examples having to do with angle similarity. So we just need to know that two angles are congruent to know that the triangles are similar. So let's look at a couple of examples. So on these examples, our question is, are they similar? So here are our triangles. And with these, we want to go with how they are drawn, or not with how they are labeled, not how they look. So they're not necessarily to scale. I'm going to call this triangle ABC and this triangle DEF. And we want to know, are these two triangles similar? Well, we know that these angles are both 90 degrees, so there's one congruent angle. So what do we need to do here? Find the other angle in one of the triangles. So let's find this angle. 90 plus 65 is 155. 155. 180 minus 155 is 25. All right, so now we have a 90-degree angle and a 25-degree angle in that triangle, 90-degree angle, 25-degree angle in that triangle. So we can say, yes, they are similar by angle-angle similarity. And if we wanted to write a similarity statement, we could say that triangle ABC is similar to triangle, which angle is going to match up with angle A? Angle F. Which angle is going to match up with angle B? D. And then finally, so triangle ABC is similar to triangle FDE. All right, I'll make this next one really easy. Same question, are they similar? So I'm going to say that this is 105 degrees. That's 105 degrees, so we're good there so far. This is 45 degrees, and this is 45.001 degrees. So are these two triangles similar? Nope, the angles have to be exactly the same. They have to be congruent. So this would be a no. Angles have to be exactly the same. It's pretty close, but it's not exactly the same. So we're going to say no on that. So questions there on angle-angle similarity. As long as two angles are congruent, then our triangles are similar. And if we needed to, then we could set up proportions between their sides, so figure something else out about the problem. All right, our second tool, our second shortcut for triangles. Side, side, side. So a lot like side, side, side for congruent triangles, we have side, side, side for similarity. We're going to say that if three sides of one triangle are we're showing that our triangles are similar. So what do you guess we're going to say it's true about the sides? They're not congruent, but they are. Well, they're similar, and when the sides are similar, what was our go-to? What was our tool? Proportional. We're going to set a proportion. So if three sides of one triangle are proportional, of our other triangle, then the triangles are similar. And remember that proportional means the same ratio. All right, so let's look at a couple of examples having to do with side-side-side similarity. So here are my triangles. We call this 5, 9, and 10. Triangle ABC. And and the same question, are these similar? Are the triangles similar? Well, all we know about are the sides. So to decide if our triangles are similar, we're going to see if the three sides are proportional. We need to check all three sides. So what side are we going to match with side 5 on this triangle? Which one? D is, so we're going to match the small side with the small side, the big side with the big side, the medium side with the medium side. So which side is going to match with side 5? 2.5. 5 is the smallest, so we want the smallest side here. So 5 divided by 2.5 is what? What do I have to multiply 2.5 by to get 5? 2. What side is going to match with side 9? 9 is the medium side. Which is the medium side here? 4.5. So 9 divided by 4.5 is 2. And then finally I'm going to match side 10 with side 5. And that's 2. So yes, by side, side, side. And I need to check all three because this third one could have turned out, to be, if this wasn't exactly 5, it could have been 2.1. And then this triangles would not have been similar. They have to, all three ratios have to be exactly the same. So now we can set up a similarity statement. So we could say triangle ABC, and it's set up nicely, is similar to triangle DEF. And I don't have to go, I wouldn't have to set up my proportions this way for 5 over 2.5. I could have gone the other direction, used the small sides on top. So 2.5 over 5, 4.5 over 9, and 5 over 10. And instead of 2, I would have gotten 1/2 for each of those. So as long as I stay consistent with how I set up my proportions, I can go either direction, big to small or small to big. Now for this triangle, what's the scale factor? 2. Going this way, it would be 2. This one is twice as large as this one. The big one is twice as large as the small one. If I went the other way, from the big one to the small one, what's the scale factor there? 1/2, right? This is half as big as it. So depending on which direction I went, the scale factor is either 2 or 1/2. And it has to do with this ratio. All right, let's look at another example. Same question, are they similar? So here are my triangles. So looks like maybe they could be, but my drawings could be off. And we want to know, are these two similar? So we know 3 sides. We need to set up a proportion. We want to make sure the sides are proportional. Well, 7 is going to match up with, well, let's do the small one first. 5 is going to match up with which side? 10? What do I have to multiply 5 by to get 10? 2. 7 is going to be the medium side. What do I multiply 7 by to get 14? 2. 11 times 2 is 22. So these would not be similar. 11 times 2 does not equal 24. So these are not similar because that one side is not in the same proportion as the other sides. All right, questions there? Important with side, 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 it's important to check, make sure all 3 sides are the same proportion. Set them up and make sure you're same ratio. It doesn't matter, again, which direction you go, as long as you go either big to small or small to big. And you can see that my drawings, these drawings definitely not to scale because this triangle looks bigger than this one. Label it. Doesn't work. All right, our last shortcut for triangles, side angle side. A lot like side angle side for congruent triangles, but a little bit different because we're talking about similar triangles. So we want two sides of one triangle they're not going to be congruent because we're talking about similar triangles, are proportional. That word proportional, that's our key word really for chapter 7, proportional. Two sides of one triangle are proportional to two sides of another. And we have to take care of this angle now. And the included angle angles are congruent. And let's remember before we write the rest, what do we mean by included angle? The angle where the sides meet, the angle between the sides. So the included angles are congruent. Then the triangles are similar. So if I draw a triangle just to show what we're talking about here with the included angle, if I'm talking about side 1 and side 2, that would be the included angle for side 1 and side 2. So our angle has to be between the two sides that are proportional. So two sides proportional, the angle between them, for the two triangles, have to be congruent. And then our two triangles are similar. So let's look at some examples using side angle side. Same question we asked before. Are they similar? So this is 7 and 5, 14 and 10. Sides, do the sides look okay for these two to be similar? 7 times 2 is 14, 5 times 2 is 10. So we need to check that included angle. So I'm going to say this is 110 degrees, and this is 109.9 degrees. So are these two triangles going to be similar? Nope. The angles are not congruent, so they're not similar. So our angles have to be congruent for our triangles to be similar. They're close, very, very close to being similar. But if we check, that would, since this angle is a little smaller, this side is going to be a little smaller compared to that side. We talked about that before. Since this angle is smaller, that angle's than this one, that side's going to be a little smaller proportionally. So it wouldn't quite match up. All right, let's look at one last example using side angle side. Same question, are they similar? I'm going to call that side 5 and that side 8, and that side 3 and that side 4.8, and 35 degrees. 35 degrees. This time we're looking okay for our included angles. Our included angles are congruent. We need to check the proportions of the sides. So what side am I going to match with this side, with side 5? 3. It's a smaller one, right? So I'm going to say 5 divided by 3, and when I calculate that out, that's 1.666, keeps repeating. And I'll check the other side, 8 divided by 4.8. And when I calculate that out, that comes out to 1.666 repeating. So the answer is yes, by side angle side. Included angles congruent. The two sides are proportional, so the triangles would be similar. All right, questions there? All right, so three shortcuts for triangles. We have angle, angle, angle. We need to show the two angles are congruent for our triangles to be similar. We have side, side, side. Three sides have to be proportional for our triangles to be similar. And we have side, angle, side. Two sides proportional, included angle congruent. Then we know our triangles are congruent. So one nice thing we can figure out, one application of similar triangles, and I just want to do an example of that, is indirect measurement. So using similar triangles, we can measure things that we wouldn't otherwise be able to measure. So let's take a look. We want to know how tall a tree is. We're in the forest. And all we have with us are a mirror and a tape measure. But the tape measure, we can't get the tape measure all the way to the top of the tree, so we can't measure the tree with a tape measure. But we're smart geometry students, and we know all about similar triangles, so we realize we can measure the height of the tree. So we're going to place a mirror 40 feet from the tree. We're going to back up five feet from the mirror. And when we back up 5 feet, we can just see the top of the tree in the mirror. So we back up just enough and we just see the top of the tree in the mirror. We know that we can measure. It is 5 feet, 8 inches from the ground to our eyes. Once you do this, you realize, oh, I know how tall, I can figure out how tall the tree is. So let's draw a picture and see what we can figure out here. So here's our tree. So this is a very tall tree. We place our mirror right here, and this is 40 feet from the tree. So right there is where the mirror is, right there. We back up from the tree 5 feet. So we're going to stand right here. So this is 5 feet. And we know from our eyeballs to the ground is 5 feet, 8 inches. So here's what I'm going to do. The light bounces from the top of the tree. It hits the mirror, and it bounces right up to our eyes. And we're going to say that the tree is going straight up. So this angle between the tree and the ground is 90 degrees. We're standing straight up, so this angle that we make with the ground is 90 degrees. And what do we know? I'm going to draw this line to the base of the tree here. Redraw this. Okay, thank you. So we're going to draw that triangle. What do we know about the angle that the light makes with the mirror when it goes from the tree to the mirror and then from the mirror to our eyes? The angles, it bounces at the same angle, it bounces off the mirror, the same angle it went into the mirror with. So those two angles are congruent. So if we look at this big triangle and this little triangle, we know that the triangles are similar by angle. It has a 90-degree angle, and we have the angle that the light makes with the mirror. Well, if we call the tree x, the height of the tree x, well, now we can set up a proportion. We know that the sides are proportional. So we say x over 5 feet 8 inches equals 40 feet over 5 feet. Matching up those two sides of the triangle and those two sides of the triangle. And we can solve for x here. Now before we solve for x, what are we going to need to do with this problem? We have 5 feet 8 inches here and we have 40 feet and 5 feet here. We need everything in one set of units. So 5 feet 8 inches. Well, let's do 5 feet. 5 feet times 12 inches per foot is 60 inches. So 5 feet 8 inches is going to be 68 inches. And then 40 feet times 12 inches per 1 foot is, when I multiply this out, 40 times 12, let me calculate that. Is 480. 480 inches. Now I can set up my proportion all in inches. I have x over 5 feet 8 inches, 68 inches. Equals 40 feet, which is 480 inches divided by 60 inches. And now I can solve this. Cross multiply, I get 60x equals 68 times 480 is 32640. And then I divide by 60, and I get x equals 544 inches. So the tree is 544 inches tall. I can convert that back to feet. 544 inches times 1 foot per 12 inches. So I'm going to divide by 12. 544 divided by 12 is 45.33 repeating feet. And if I wanted to convert that 0.33 feet to inches, a third of a foot is 4 inches. So that would be 45 feet, 4 inches. So the tree is 45 feet, 4 inches tall. So this is one way that we can use similar triangles to do indirect measurement. Questions on that example? All right. So let me pass your folders back. we'll go over